Hi class, welcome to lesson 2, significant figures. By the end of today, you should be able to describe and use the rules for determining the number of significant digits in any number and explain how significant digits relate to the accuracy of a measurement. Make sure you're taking notes. You have a Regents Chemistry reference table and a calculator. Let's get started. So the first thing we need to ask ourselves is what exactly is a significant figure or a significant digit? So significant figures relate to measurements. In science, we use a lot of numbers, and so we report those numbers with significant figures. The numbers in which we write down or report are called the significant figures, and they always include all of the known values of a measurement plus one estimated place value. So if we were to go and measure the length of this pencil in centimeters, what we can see is we're sure that it is definitely 4.7 centimeters because it's somewhere between 4.7 and 4.8, but then we need to estimate approximately how far in between 4.7 and 4.8 this length is. So two acceptable measurements could be 4.72 or 4.73 centimeters. The estimate will and can vary from person to person. So again, when we measure, it's really important we measure one more place value than is seen on our instrument. So here again, we have rulers. On the left, the rulers include the tenths place. And so our measurement has to include the hundredths place. So this nail has a length of 4.39 centimeters according to ruler A. Now, if you thought it was maybe 4.38, that's also okay because that last digit is an estimate. On the right, this ruler has less precision, so it is only marked to the whole centimeter. So according to this ruler, the length of this nail is only 4.3 centimeters. Now, if you thought it was 4.2, you're also correct. The important thing is the measurement that can be recorded with this instrument can only go out to the tenths place. So notice how we have the same nail, but since we have different rulers, the better ruler on the left has more place values in the measurement than on the right. Again, science is a system, so this is the system we use for measuring one place beyond. Okay, so let's practice measuring one place beyond with several instruments. So here we have the volumetric instruments called graduated cylinders. Recall that when you read a measurement from a graduated cylinder, you always want to read from the bottom of the meniscus, that sloping region. So we can see that the graduated cylinder on the left has less divisions. So its measurement, I'm going to estimate it to be approximately 4.7 milliliters of liquid there. Now, since the tenths place is my estimate, you could estimate 4.8 milliliters and you would still be correct. But the most important thing is all measurements with this graduated cylinder must include a tenths place. Now on the right, we have a graduated cylinder with more divisions. So we need a number that reflects this better instrument. So here we have 4.7 again, but I think it's directly on the line. So I'm going to say 4.70. So what's really interesting is that in math and in chemistry, these quantities are the same, right? 7/10 is the same as 70/100, but the precision of each of these measurements is different. And so we can tell from 4.70 that we have a better instrument than we have with 4.7. Here, let's try again with these thermometers. When we look on the left, the thermometer has the tenths place, and we want to go and record the temperature in degrees Celsius from the top of the liquid there. And so here on the left, we have approximately 0.45 degrees Celsius. So here on the right, what we can see is that we have only the ones place marked, and we're going to read from the top of the line. We see that we're somewhere between -2 and -3. We appear to be a little bit closer to -3, so I think that I would estimate this temperature to be -2.7. Now, if you went and included a temperature of -2.6 or -2.8, that would also be acceptable because the last place value can vary from person to person, though we can obviously tell that it's not like 0.0. So although it's an estimate, it needs to be reasonable. So looking here at this gauge, which of these measurements would be acceptable related to this? Take a minute to pause the video and find the 2 acceptable measurements. So what I see here is that this is a measurement somewhere between 98 and 99. We only have ones place marked, so we're going to need a tenths place. And so here are our 2 acceptable measurements. Now, what do you do if you have a digital reading? Digital readings, the last digit is the uncertain digit, so it is the estimate. And in labs, sometimes when we use our digital balances, you might notice that that last digit might go up and down even when you're not doing anything. You just want to make sure that you catch it at one point or its most steady point. So take a minute and try and decide the measurement of the liquid in this graduated cylinder. You'll have to record your answer in your homework on Google Classroom. You'll also have to include the measurement of the pressure of this instrument on Google Classroom. And finally, make sure that you understand the value of each of the divisions on this beaker and record the measurement of liquid in this beaker on Google Classroom. So by now, you should be able to explain how significant digits relate to the accuracy of a measurement, or how different instruments with different numbers of divisions should always give slightly different measurements. Now we're going to talk about the rules for assigning significant figures to any number. Take a minute to pause the video and write down these 4 rules, and then we'll talk about them. Okay, so let's see if we can apply each of these 4 rules. So in the first rule, we have that all non-zero digits are significant. So we don't need to worry about counting significant digits. If there are no zeros, then all the digits are significant. So in the number 3,985, this number is written with 4 numbers, so it is 4 significant digits. While the number 3.3 is written with 2 numbers, so it has 2 significant digits. Rule number 2 is also quite easy. It's called the sandwich rule. So when a zero is in between 2 non-zero digits, it will always also be significant. So the number 509 has 3 digits with the 0 in between. So this has 3 significant digits, versus 1002 has 4, as does 2.006. That is 4 significant digits. So the tricky part about significant digits happens when the zero either comes in the front of the number or in the back of the number. So the leading zero rule says that zeros that are placed in the front of a number are never significant. They're just placeholders. So they show you how small the number is, but they don't work back and show the divisions on an instrument or the graduations on a ruler. So we don't count zeros that come before a non-zero digit. So in this very small number here, we can see that none of the leading zeros are significant, but the 3 and the 4 are. So this value has 2 significant digits. Now, again, we have another small number in example G, and those leading zeros are not significant. So this has 2 significant digits. You do need to be able to combine the various significant digit rules. So we know that zeros that come in front of non-zero digits in a number, so numbers less than 1, are not significant, but we have to go back to the sandwich rule for this example in H, as the sandwich zeros are significant. So this value, the first 0 is not significant, but the rest of the digits are. So there are 4 significant digits in example H. And the final significant digit rule, called the right rule, says that trailing zeros, or zeros at the end of the number, are only significant if there is a decimal point in the number. So when we look at example I, we see there's a decimal point, so that 0 is significant, as is every non-zero digit, so that has 5 significant digits. Again, you will need to combine the rules sometime. So in example J, we can go back to rule 3 that the leading zeros don't count. So the first 2 zeros of the number are not significant, but since there's a decimal point, the ending zeros are. So this number, 0.0830, has 3 significant digits. And for letter K, there's no decimal in the number. So this number 250 is written with no decimal. When there's no decimal, then the ending zeros are not significant. So this value has 2 significant digits. Although the 4 significant figure rules we just discussed are always true, I find them a little hard to remember. Let me show you a shortcut I like to use called the Atlantic and Pacific rule. The Atlantic and Pacific rule are based on the locations of the Atlantic and Pacific Ocean relative to the contiguous United States. To use the Pacific rule, if a decimal is present in a number, start looking for the significant digits on the left. Once you hit your first non-zero digit, that is your first significant digit. Continue moving from left to right until you've counted all the remaining digits in the number. So this value has 3 significant digits. The first non-zero digit is 3, and we continue until we're done with the number. Use the Atlantic rule when there is no decimal present, but instead the decimal is absent. Start on the right side of the number. Once you hit your first non-zero digit, that is your first significant digits, continue counting until you've counted all of the digits in the number. Here you can see again we have 3 significant digits. Now I'll show you how I can use the Atlantic and Pacific rule in all the examples we did earlier. So starting with this number, you can see the decimals present. Since there's a decimal, we'll start at the Pacific Ocean side of the number. As we approach, we'll collide with the first non-zero digit, which is a 3. So our significant digits are here. This number has 4 significant digits. This number also has a decimal, so we'll start on the Pacific Ocean side of the number. This number has 2 significant digits. Now when we look at this number, notice that it is written with no decimal place. So we're going to approach from the Atlantic Ocean side of the number. The 4 is the first significant digit, but we have to count all the rest of the digits in the number.
This number has 4 significant digits. When we look at this number, again, there's no decimal. Start from the Atlantic side. This number has 4 significant digits. Now, when we look at this number, notice the decimal's present. Approach from the Pacific Ocean side. This number has 4 significant digits. Here, the decimal's present again, but we're starting with zeros. You have to start counting significant digits at the first non-zero digit. So we're going to discount these numbers. These are not significant. And this is our first significant digit, so this value has 2 significant digits. Now, these zeros are still important. They tell us how small the number is, but they just weren't part of our instrument. And so we're certain of the 3, and we've estimated the 4. Here, the decimal's present again. We're going to go from the Pacific Ocean side. This has 2 significant digits. Again, we have a decimal present, so we're starting in the Pacific Ocean side. And so once we start counting, you have to count all the rest of the digits. So this has 5 significant digits. On my measuring instrument, I'm certain of the 5, and I'm actually guessing that this is a measurement that lands exactly on the 5. So this 0 is my estimate. And finally, here again, we have a decimal place. So as we start counting, we have 3 significant digits.
By now, you should be able to describe and use the rules for determining the number of significant digits in any number. It doesn't matter if you memorize the 4 rules or if you use a shortcut. Just be able to report how many significant digits are in any value given to you. Are in any value given to you. You've now reached the end of lesson 2. Make sure you've taken good notes. Complete your homework. Bring any questions you have to class, and I'll see you soon.